So you can hear me. The mic is working. I just need the PowerPoint on. So could you turn it on? But thank you for the nice introduction. Is it working? What? Yeah. Can you hear me? Please raise your hand on the back row. Yeah, okay, good. So now we just need the PowerPoint to be working, and then I'll be going. But thank you to the organizers for inviting me to come and speak at this very special place, interesting conference. I'm going to talk about the safety of nanoparticles or nanotechnology, and I'm going to touch upon whether there are reasons for concern. And just about my background, I'm employed at Aarhus University at Department of Environmental and Occupational Health, or Medicine, at Public Health, and work as a research scientist in the field of nanotoxicology. So I just need the thing to work. Should it be switched on? Ah, something is happening. Yeah, okay. Thank you, Frank. Okay, so this was the introduction slide, so I just mentioned it all. But the problem is there a nanohazard? So this is a brief outline of the talk. What are engineered nanoparticles? You probably have very different backgrounds, so I'll just touch upon that. Why are they used? What are the potential concerns about the safety? I will, throughout the talk, focus on risk assessment also. How do you evaluate a compound and determine whether there could be potential risks? And I'll also try to say a bit about regulation of nanomaterials. So it all more or less gained speed in January 2000. There was this article in Chemical and Engineering News stating that nanotechnology is the next big thing. And what you actually see on the picture is the word nano USA written by carbon monoxide molecules. So these molecules are around 3 or 4 nanometers. And not only the ability to manipulate molecules at this scale is fantastic, but also the ability to actually visualize it by very, very high power microscopy. So in this case, it's probably atomic force microscopy. So it's nothing like the microscopy you learned about in school. So this is the nanoscale. It's difficult to comprehend if you don't work with it on a daily basis. So you can describe it like if you have a particle that's 1 nanometer in diameter and you compare it to a football, then the size difference is the same as if you compare the football to the Earth. So it's very different sizes. On this scale, you see that on the left, there's a human hair sample, and you can see that it's around 100 micrometers. That is the same as 0.1 millimeter. At the other end of the scale, you have 1 nanometer. Nanoparticles are generally defined as particles with at least 1 dimension between 1 to 100 nanometers. And you can see cells are much bigger than nanoparticles. Cells are micrometers, so they are around 1,000 times larger than nanoparticles. And on the nanoscale, you also have biological macromolecules. You see a cartoon of a protein structure, and this is also on the in the nanoscale. Also, certain viruses, the very small viruses like poliovirus, is on the nanoscale. It's shown by electron microscopy as 30 nanometer. So what is a nanoproduct? It comes in 1 dimension, 2 dimension, and 3 dimensions. So first you see a bulk material. It could just be any material, and on the top there's this yellow surface, and that's the nano surface. So it's in 1 dimension nano, and meaning that the surface is a maximum of 100 nanometers thick. And this will give this material different properties. You can also have nano in 2 dimensions. So you see in the middle figure that you have a very long structure, but it has 2 dimensions that's in the nano range. So this could be a very, very thin fiber, for instance. And finally, you have full-blown nano. That's in 3 dimensions. You have the nanoparticles. All dimensions are below 100 nanometers. The exciting thing about nanotechnology is that when objects are below the 100 nanometers in size, they can exhibit very unexpected chemical and physical properties. So here you see on the lower panel, you see electron microscopy photos of different nanoparticles. So you have silver particles and you have some gold particles also, different sizes. To the right, you see silver nanoparticles, 40 nanometers in size. They have a blue coloration. If you go to the left part of the figure, you see a red coloration. And these are still silver, but it's in a different shape called nanoprisms, and they are a little bit larger. So the color can change depending on the size. Also, other properties, such as chemical properties and physical properties, could change. Especially the reactivity of the particles is very different compared to the bulk material. And it could be other things like melting point, conductivity, etc. I'll just come back to some of it later on. So small is different. And one could raise the question, is gold golden? Actually, already in ancient times, they knew about nano. They just didn't know exactly, but they knew that it worked somehow. So here you see a gold cup to the left. And that's actually gold color. It's pure gold. To the right, you see a glass embedded with gold nanoparticles. And this was made already in ancient times. They knew how to make these particles. They just didn't know how it worked. And if you shine light on this cup, it will be red in color, and that's not gold color. So already then they knew. And now to the applications of nanotechnology. What are we using it for? First of all, there's textiles and fabrics. You've probably heard about the nano socks or the nano silver socks. Those are socks impregnated with silver nanoparticles, and these silver nanoparticles will release silver ions that are very toxic to bacteria. So you will this will prevent your socks from smelling. You could also have different surfaces on the fabric, thereby enhancing resistance to water, etc. You probably saw the nano cover commercial some time ago. I'm not sure it worked, but they tried to do it. In sporting equipment, you have golf clubs, tennis rackets. You can use different nanocarbon materials to increase or reduce the flexibility and the strength of the material. Going to the top, in food packaging, most people know that if you have a beer in a clear bottle and you put it in the light, the UV light will degrade substances in the beer and cause it to taste horrible. We call it a sun beer in Denmark. But if you have special nanoparticles embedded into the glass or the plastic, these particles can actually absorb the UV light and in that way protect the food inside the packaging from being degraded. Another very important area is within pharmacology or within medicine as a way to make targeted drug delivery. So what is actually investigated in the moment is to have a nanoparticle and make it deliver some kind of chemotherapeutic. So if you have cancer, instead of just ingesting the chemotherapeutic, you will have nanoparticles coupled to the therapeutic, injected into the bloodstream, and the nanoparticles will find their way to the tumor, maybe prostate cancer, and they will only affect this tissue. So you wouldn't lose your hair from this treatment because it would only go to the tissue in question. Also, nanoparticles are used for imaging. So small magnetic iron oxide nanoparticles can be injected into the bloodstream and used for MRI imaging. And some of these particles are actually approved by the Food and Drug Administration in the US. Finally, I'll just touch upon cosmetics and personal products because several types of cosmetics contain nanoparticles. And the most famous one is sunscreen. Because in old days, you had sunscreen and you would put it on your hand and you would turn white because of the physical filter from the micron-sized particles inside. Now they still use the same substance, but the particles are much smaller, and therefore the solution becomes translucent, and you do not turn white. You just keep your natural skin color, and these particles are very efficient at scavenging UV light. Going from the applications and to the commercial use of different materials in nanotechnology, you can see in the figure that silver is the compound which is used in most of the nano-consumer products. I should say this doesn't say anything about the quantity of the material. It just says how many different consumer products it's used in. And it's from March 2011, so it would probably be 500 instead of 300. But also carbon, titanium, silicon, zinc, and gold are widely used. You see the nano-silver sock to the right. They also tried to impregnate washing machines with silver nanoparticles. Then they would release ions when they washed the clothes to provide an antibacterial effect. However, this is now categorized as a pesticide in the US, at least it was last time I looked. Those are the compounds in question, primarily in question. So in 2007, Donaldson and Seaton from Napier University in Edinburgh published this review paper where they talked about, they mention all the promising advances in nanomedicine, using nanoparticles and stuff, but they also question, could there be toxic effects of the nanoparticle exposure? Could it be a Janus phase? They come to the conclusion that the benefits of nanoparticles is way higher than, are way greater than the potential toxic effects, but that's still in question. Having raised this issue about the safety, I just have to touch upon risk assessment. What is risk assessment, actually? And coming from the field of toxicology, this is what we do. First, you need to identify the hazard. So you can have some kind of compound, and you would test it in cells or in animals, see is there some kind of adverse effect of this compound. The next thing to do is to look at the dose response. So you would give different doses of the compound to see if there's one certain dose where there's no effect. So that's where the dispute is, for instance, around fluoride, as you mentioned, as was mentioned in the last talk, is where is the no effect level? What is the dose where there are no adverse effects? Okay? So that's why dose-response relationships are very important in toxicology and also in nanotoxicology. Then we come to the exposure assessment. This is also very, very important because you can have a hazard, you can work with very dangerous chemicals. For instance, in industry, people do that, but they wear protective equipment. They use gloves and they use respirators and stuff, so they are not exposed to the dangerous substance, and therefore they have no risk of being sick, okay? So exposure assessment is very important. And finally, you characterize the risk by combining the hazard and the exposure. And this you would like to do both for the human effects, but also for the environment. So this was just the intro to risk assessment. Now turning back to nanoparticles, is there a health risk? The problem with nanoparticles is that it's artificial. It's a little bit exotic to the public. We have little knowledge, or at least people feel we have little knowledge. It has improved the last couple of years. We have no experience, is at least the public thought, and there's a fear that it becomes uncontrolled, like the GMO scandal, the gene-modified organism scandal. Also, we know that some particles are actually toxic. You can see the danger sign saying asbestos is toxic, and we know that certain types of asbestos induce cancer. So there are several concerns, but also the area of particle toxicology, the toxicity of particles, whether it be large particles or small particles, has actually established a lot of relationships between disease and particle exposure. So what you see in the picture is, for instance, I don't have a pointer, but you can probably see it. There's cigarette smoke. There are lots of particles in cigarette smoke. You see some particles from diesel exhaust on the front picture, these small dots. Those are nanoparticles from diesel exhaust. And you also see on the picture there's diesel exhaust. But also we have forest fires providing fine particles or ultra-fine particles, also called nanoparticles. So we have different sources of particles, small particles and large particles. And some of them are natural, and some of them are man-made or anthropogenic. And the man-made ones could be unintentional, like diesel exhaust, but they could also be intentional, like engineered nanoparticles. So I'll focus on the intentional engineered nanoparticles, but just to tell you that we have a lot of knowledge on other types of particles. The problem with natural particles is that these particles are not well defined as the nanoparticles from industry. Instead, particles in the environment are very, very complex and often thought to be more dangerous than engineered nanoparticles. But we would expect to see some of the same effects. And what are these effects we could expect based on the knowledge about previous studies on natural nanoparticles or particles in general? You see the lung to the right, and what this figure illustrates is that depending on the size, these are microns, depending on the size, you affect different parts of the lung and different parts of the body. And it's clear that the smaller the particles are, the deeper can they penetrate down into the lung. So if you have large particles, they will stay in the upper respiratory tract, but if you have very small particles, they will go all the way down and could actually also go from the lung and into the bloodstream. So now you have a systemic effect instead of just a lung effect. And that's what people found about the environmental nanoparticles, that cardiovascular diseases could be associated with diesel exhaust, for instance. They found inflammation in different tissues. Cancer has been associated with exposure to these particles. Neurotoxicity, because the particles could go into nerves, for instance, through the nose and travel along the nerve axons. And finally, we are always worried about the unborn child, but I'll just touch upon that later. So we have lots of reasons to think there might be some problem. But why are nanomaterials, or very small particles in general, why are they potentially toxic, dangerous? The big hypothesis is that it's due to the large surface area of the particles. So to the left, you can see you have a 1 centimeter cube. This cube has a total surface area of 6 square centimeters. Now you cut this cube into 1 millimeter cubes, and you have a surface area of 60 square centimeters. But if you cut them into 1 nanometer cubes, you have a surface area of 60 billion square centimeters. So it's a very large surface area. And with this large surface area, there comes a huge reactivity of the materials, but also there's the possibility of a very huge surface area to interact with components in the body. Proteins and DNA and stuff if they go into the cells. This made Günther Oberdurst, an old guy in particle toxicology, suggest in 2005 that we should have a new risk paradigm. He made this paper on nanotoxicology, an emerging discipline evolving from studies of ultrafine particles, the environmental particles. And what he actually concludes in this paper is that the toxicity of nanoparticles and the bulk material of the same compound, so it's silver, big silver, small silver, different toxicity. And therefore we have to have different, therefore we have to determine the properties that are significant for nanoparticles toxicity. And maybe we couldn't say, oh, I inhaled 5 grams of nanoparticles. Maybe we should say, I inhaled 60 billion square centimeters of nanoparticles, right? So we have to find out, how should we decide what is the dose? This was in 2005, he came with that paper. Now I just did an article search on the keywords nanoparticles and toxicity. And I did it in PubMed. That's a database everybody uses for these kind of studies. And you see, in 2005, there were maybe 50 studies available. It came out that year. But in 2011, you had more than 1,000 studies published in 1 year just on nanoparticles and toxicity. So we have loads of data. But there are some issues with those data, and I'll just touch upon that also. Turning back to the risk assessment, first of all, we had to do the hazard identification. So one way to do it is to look on the prevalence of disease in humans. So you could, for instance, take a factory that produce nanoparticles. This wouldn't be in Denmark, because in Denmark we practically don't produce nanoparticles. But you could go to this factory and then look at the workers and say, okay, they walk around inhaling nanoparticles. Do they have any specific diseases? This is time-consuming, it's expensive, and you need places where people are actually exposed to the nanoparticles. So we don't have any data on this. We don't have any epidemiological data on engineered nanoparticles yet. So what people do is that instead they do experiments. In the old times, doing toxicology, the first you would do was to take animals, probably rodents such as mice or rats, and you would inject the compound into the animal and see, does it die? When are 50% of the animals dead? Today, we have a strategy called the 3 Rs that say we should reduce, replace, and refine animal experiments. In our lab, we don't do animal experiments. We do all our work in cell lines. So we just grow the cells in the lab, and we do experiments that way. But still, you need some animals probably, but at least we don't do it. Another way is to do it in silico. So you could have a group of nanoparticles that look very much alike, and you could say, do they have the same effects? Then maybe you could group different compounds, and then you would just need to know about one of the compounds in the group, because all the other compounds are supposed to have the same effect. That's called in silico analysis, or QSAR. So that's different ways to do hazard identification. That's what people did in all those many, many papers you saw had been published. So this is a key slide in this presentation stating that it's a little bit busy slide, but the same properties which make nanoparticles interesting could potentially make them harmful. So I'll just try and walk you through some of these things. So in the middle you have a nanoparticle. It has different physical and chemical properties. And you could, for instance, take the composition. Some nanoparticles have a core of one substance, and then they have an outer shell of a different substance. One of these kinds of nanoparticles are called the quantum dots, and these contain cadmium in the inside. And it's obvious that if this cadmium leaks out of the particle, then it's toxic, because we know that cadmium is toxic. So the composition is important. Another very important thing is the crystal structure of the compound. So you can have, in this case, titanium dioxide. So titanium dioxide was the thing that was in sunscreen, among other things. But there are different forms of titanium dioxide, several different crystal forms. It's all the same chemical formula. It's called TiO2, but it's different crystal structures. And the one we use in sunscreens is called rutile structure, and it absorbs and scatters UV light, and it's non-reactive. But there's another form called anatase, and this form is actually used for products to spray on windows. It has been very popular to spray this formula on car windows, because the anatase form, when it's hit by UV light from the sun, then it will make some very reactive intermediates called reactive oxygen species, free radicals, and these radicals will simply burn off whatever dust and stuff comes in contact with the front window on the car. So that's very smart. And also, because it's nano, normally titanium dioxide in micro-sized particles will be a white dust. But when it's nano, it's translucent. So you can still just look through the front window. Okay. Then about the solubility. Thinking about asbestos, one of the problems with asbestos was that asbestos just stays in the lung when you inhale it. It doesn't get out. You can't excrete it. And there are some issues about some nanoparticles called carbon nanotubes. Those are the kind that, for instance, could be in tennis rackets and stuff like that. Those are very biopersistent. So if they are longer than the cell, and they get into the lung, and they can't be degraded, they would just sit there forever and forever and forever, increasing or inducing inflammation in the lung. So that would be a problem, but it's still under investigation. Other compounds, such as silver nanoparticles, are actually dissolving slowly, and silver ions can be excreted through the kidney and urine. So it's an important factor. Okay, so I'll not go through them all, but just touch upon two more. The size, as I mentioned, is very important in terms of the uptake, in terms of the translocation, for instance, from the lung and into the bloodstream, but also from the skin into the bloodstream. Fortunately, most data show that nanoparticles from sunscreen does not penetrate through skin and into the bloodstream in intact skin. Also, the uptake is important. Very small particles are easily taken into cells. So if they gain entry into the body, they will go into the cells, and what happens there? Are they degraded or are they biopersistent, like the asbestos? Finally, the shape is important, because if the particles are longer, if it's fibers and they are longer than the cell will try to take up the particle called phagocytosis, but it will become frustrated phagocytosis because it can't take it up. The particle is too large to be inside the cell. And then substances will leak out of the cell, causing inflammation. But also we have other kinds, apart from nanotubes, we also have spikes and stuff on the nanoscale. Okay. So just a little bit theoretical slide, because people would probably like to know if there's some kind of general mechanism for nanotoxicology or nanotoxicity. And one of the things that come up very often in these kind of studies is the induction of reactive oxygen species. So you've probably heard about that if you eat vitamin C, you will have an improved antioxidant defense. What happens in the cell is that normal cells have a low level of oxidative stress, a low level of reactive oxygen radicals, but still there is a certain level all the time of reactive oxygen species, because we have to use air to sustain metabolism, to walk around. But if you have a little bit of nanoparticles inside and they induce reactive oxygen species, you will see antioxidant defenses. We see that for some particles, but not all. If the antioxidant defense of the cell is not enough, then you will have inflammation, and finally, if that doesn't cure it, you will have cytotoxicity and the cell will die. So this is a general paradigm, but it turned out that this is much, much too simple. So it's just to give you some kind of feeling on what's going on in the field. And why are reactive oxygen species so interesting? Well, it's been implicated in almost every disease. At least, so people worry that if you have induction of increased oxidative stress in the cells, you could have, it's been related to Alzheimer's disease, Parkinson's disease, even arthritis, diabetes, you name it, it has been linked to it. But none of these associations are certain. These are just clues. Could it be related? But that's why we're so interested in this particular pathway, reactive oxygen species. So now I'll just turn to the problems testing nanoparticles. The first two I'll just come back to in a minute, but it's about unrealistic doses and how to measure the dose. And the next are, what are we actually testing? The problem is that some assays do not work because these nanoparticles are so reactive and have very special characteristics, meaning that they interfere with the experiments we're performing. So when we want to measure something, the nanoparticles sometimes interfere with what we are measuring. So this part has been very difficult, but fortunately, the OECD is now validating a lot of protocols to do experiments to ensure that we can characterize the potential hazard from nanomaterials. But turning back to the thing about doses, as I also mentioned in the start of the talk, the father of modern toxicology, everybody should know him if they like to learn about toxicology, is this guy Paracelsus. He stated the sentence below, but it's a modification because I added the word timing. But he says that all substances are poisons. There's none which is not a poison. The right dose and timing differentiates a poison from a remedy. So we could just take vitamins. If you have too few vitamins, you will get ill. If you have too much vitamin, you will get ill. So you have to find some way in between. And also, everything, and this is actually his primary message, everything is toxic. Even water. We have cases with persons in the US, for instance, that die from drinking water because they want to flush out the body. And also the timing is important. So we had different cases with pregnant women eating stuff and the babies were not healthy. So that's only when you're a baby. Some compounds only are toxic when you're a baby or you're a child and stuff like that. So the timing is also okay. So finally, the dose-response curve, where you have the dose. So what we are really interested in is if there's some kind of threshold, and that's general in toxicology, where there are no observed effects, also called an NOEL, no observed effects level. So we just want to see, is there a dose response in terms of adverse effects, and when is the compound safe to use? Because we can't ban all compounds. We have to use some compounds in the daily life. And that's why we have to find the place where there's no effect. And also a thing that complicated the study of nanotoxicology was the nanoparticles that people tested. So you can see here you have carbon nanotubes from cheaptubes.com. These tubes could come relatively well dispersed. So if a cell encounters a single tube, it will try to engulf it. But if these tubes are just agglomerated together in one big ball, and they tend to do, then the cell will not even try to eat it because it's just too large. So it's very important to characterize the materials you're testing, and that's what a lot of people didn't do in all the studies I showed on the figure showing publications. Also, you have a picture of titanium dioxide nanoparticles from NanoAmor. They love nano. Apparently, they state that it's 10 nanometer size, but you can see huge particles that are 100 of nanometers. And to the right, you see silver nanoparticles that should be round, but apparently one was misformed and now it's elongated instead. And that could potentially mean a lot to the toxicity. So that's why we're still fumbling around trying to find out, is it toxic or not? That's because people didn't characterize, or part of it is that people didn't characterize the materials properly. Okay, so now we came to the final one of the risk assessment, namely the risk characterization. So the risk characterization is the hazard times the exposure. And issues to consider in this risk characterization is the characterization of the nanoparticles. We just talked about that. But also the relevance of different exposure routes. How are we exposed? Through the skin, through the inhalation, through injection, from the environment at work, from consumer products, etc. All this must be estimated somehow. And also, how does the particles move around in the body? How do they act on the body? And stuff like that. So I'll just turn to routes of exposure. You have the synthesis of nanomaterials in the upper left corner. And you can see these nanomaterials can lead to production of consumer products, and then the general population will be exposed through these consumer products. Another way of exposure is the people who actually make these nanoparticles. They will be exposed to the particles at work. Two things about this. People who work with nanoparticles normally wear protective equipment, so they shouldn't be exposed unless it's taking place somewhere in a country that doesn't consider this relevant. Exposure of the general population could sometimes be a problem, in particular with the sprays, because then you will have an aerosol coming out and you could inhale the particles. But actually, most of the consumer products have the nanoparticles embedded inside a matrix, and they will not be released to the person using it. And then finally, we have the environmental exposure. So that's another story. Turning to the framework for assessing risk of manufactured nanomaterial. So the problem was that we had new type of substances. Even though we had regulations for silver, bulk silver, we have to establish whether nanosilver is the same as bulk silver or whether it's actually different, because normally we just say silver is silver. Now we came to that it's a new type of substances, and there's no or limited information on hazards. There's no information on the exposure either. So the solution could be these two. The first is the precautionary principle. So when you apply the precautionary principle, you say, we assume that this compound is a hazard, and you have to take every measure not to be exposed to the compound. But that's very tough principle, because it will just block development within this particular substance. Another way to do it is to make risk assessment frameworks, like recently done in Denmark. I didn't do it, but my colleagues at the DMU did it, and it was published by the Ministry of Environment. So they proposed that in the project called NanoRisk, that you have different color codes for the exposure. So people can see, oh, is this a red light or a yellow light or a green light, like a traffic light. And then what they do is they categorize different nanomaterials. So the bulk form is no problem. If there's a nano surface, then it's no problem, because you won't really be exposed. And also if you have a brick with nano inside it, you will not be exposed to it. But if you have nanoparticles on a surface, maybe you should start to think about whether these particles could go off and expose the consumer. And especially nanoparticles suspended in liquids or airborne nanoparticles should be regarded as significant way of exposure, or you should have the red light turned on if you're exposed to this kind of nanoparticles. Okay, so I'm more or less rounding up, but risk assessment paradigm. Being in this forum, I also have to say that scientific committees use the framework to the right. So they have the exposure and the hazard, and they assess the risk. But in the public, sometimes, and also the NGOs sometimes, risk becomes one big bubble, and the hazard is confused with the risk. So it's very important to always remember the exposure. And you will see that in the media often. So I had some stuff on regulations, but due to time, I'll just more or less go very brief on this slide and then round up. So just to say that there are a lot of work going on in the EU, and we're regulated by the EU, right? So there are different committees, Committee on Novel Materials, Committee of Safety in Cosmetic Products, Safety in Food and stuff, and they all come with these evaluations, continuously monitoring what is going on and making sure that industry does not do anything that could harm consumers. Yeah. Finally, what I didn't discuss in this talk was the environmental effects. And maybe this in some instances is worse than the human effects. So if we consider there are particles that get dissolved, and then we have the very biopersistent particles. The very biopersistent particles in nature, if they get into nature, the environment will normally just aggregate and form large aggregates, and it wouldn't be a true risk to anyone. But the particles that dissolve, such as copper nanoparticles and silver nanoparticles, these particles actually dissolve, and the product that comes from dissolving the particles could be quite toxic. In the case of fish, we had a study at Aarhus University showing that it's generally known that silver ions are very, very toxic to fish and aquatic organisms in general. But in this study, we compared silver nanoparticles with silver ions, and we could see that silver nanoparticles were also toxic to the fish, but it's depended on the dissolution of the particles. So the true toxicity was caused by the silver ions. And this is actually already regulated in Denmark. Also, earthworms and these kind of organisms are vulnerable to ions from different nanoparticles. So the environmental effect, we don't know much about them, but we should be very aware of the particles that could dissolve. Okay, so I probably just confused you a lot about this nano stuff, but I'll try to round it up in a conclusion, and then you will just have to decide for yourself what you think. But what's for certain is that nano is not one thing. Nanoparticles are different, and they are as different as ordinary chemicals. And some nanoparticles may be toxic, but a lot of nanoparticles for sure are not toxic. Final conclusions are difficult to make due to the lack of human data, the epidemiology part, and nanoparticle interference with ordinary test systems experiments. Exposure is likely to be low from consumer products, especially when the particles are embedded inside the product. But in very few products, such as the sprays, it could be a problem. A regulatory framework is being established. The area is being monitored by the EU and national agencies. However, I should say, as a scientist, that more research is needed, because I'm dependent on funding from the state, right? So I should advocate for more research. But I also generally think that more research is needed, but it has to be high quality research. Okay, so any questions, I'll be happy to take them in the field of toxicology in general, or nanotoxicology, or nanotechnology. Yeah.
How about particles from laser printers? I've noticed that when I use laser printers, I always get a cough.
Yeah.
And I need to remove them from my whole working environment, because obviously they're causing the cough. Yeah. I'm not like, it's coming back right now during this lecture as well, but What can you say about those?
That you shouldn't be in a room with a laser printer when
Obviously.
you shouldn't allow yourself to be exposed to the particles.
But these are all classified as nanoparticles, right? They're really, really tiny.
Yeah, but it's the unintentional part of nanoparticles. That's why I didn't really go into that. I mean, these particles, that's a byproduct of printing. So they weren't, it's not particles produced just to do something. It's unintentional. But it's true, there's a debate about laser printers, and the general advice is you shouldn't be in the same room as the laser printer. Yeah.
Can you get neurological diseases from nanoparticles?
Sorry?
Can you get neurological diseases from nanoparticle if they go into your nervous system or into your brain?
Yeah, that's a really good question. So we know that some viruses can enter the nervous system, right? Like herpes, for instance. So we worry about that the particles can also go into the nervous system and somehow affect it. We know that some of the particles are very good at conducting electrical conductance. So they might disturb electrical signals in the nerve, but we have or they could have various effects, but we don't really know about it. There are studies that have found translocation of nanoparticles through the top of the nose and up through the nerve, but they didn't find any specific adverse effects. And I think the big problem is that if you get a neurological disease like whatever, this kind of disease is often multifactorial. So it's not just the nanoparticles, it's you have to have the wrong DNA and be exposed to the nanoparticles and maybe eat fish or whatever. So there's a lot of factors, and that's why we haven't solved the question yet. So I'm not able to answer better than that, but I'm not aware of any studies linking it directly.
Is it your assessment that that it's a better scrutinized area than, for example, microwave, as we heard yesterday? Is it under better research and risk assessment?
Yeah, I think so. I should say that nano, in general, is a buzzword in toxicology. So you have just seen a boom of publications, and I doubt you will find as many studies on microwaves as you will on nano. When you go to the big international conferences, they will have a whole track just on nano. I just went to China last week, and they had a whole conference, just Nanotoxicology 2012, and we just discussed nanotoxicology, people from all over the world. So I think it's a very huge area which you don't find compared to microwaves.
Yes, first question. I read somewhere that nanoparticles have the ability to pass through the brain-blood barrier. And the second is that now there are ethical discussions about the ubiquitous healthcare system that will use sensors in the human body and around the healthcare taker. And isn't it based on nanotechnology, and couldn't it become a danger for the patient in the long run?
Yeah, okay, I think that was two questions in one, but I'll try to ask the first one first. The first one was about, blood-brain barrier, yeah. Okay, so it has been shown, for instance, for silver nanoparticles in a model system that they could pass the blood-brain barrier. But this was a model system where you make an artificial blood-brain barrier in the laboratory, in the cell lab. So it's very difficult to say if this would happen in real-life situations. So you have to do animal experiments. You have to have a whole organism to really address this question. And I'm not aware of anybody who did a well-conducted animal study and demonstrated this. But it's a very interesting question, and we're actually working on this specific thing at the moment together with China. So hopefully we'll have an answer within 1 year. Yeah.
Ja, kunne du oversætte? Jeg har lige set, der er en høring på vej fra EU omkring alt det her. Og ved du noget om den, og kunne du sige sådan lidt, hvad skal vi lave som høresvar? Altså, det er sådan noget, jeg tænker på lige nu.
Yeah. Okay, just translating the question. There will be a hearing in the EU, presumably soon, and should we make some kind of response to this hearing? Actually, I must say I'm not aware of an upcoming hearing, but I have a colleague who is involved in this kind of EU work. But I think the area is very well covered by the Danish NGOs. I had a meeting with them in the Engineering Society, and I got the feeling that they, magazines like Tink and stuff, they will really try to be certain that nothing can happen with the consumers. So I think it is covered in the Danish NGOs.
I'm a nurse.
Yeah.
And I work with all kind of drugs. And already we are injecting drugs with nanotechnology in people. And I'm rather shocked to hear that you say that the brain-blood barrier is not tested in laboratories before we injected this kind of drugs in people. I'm rather shocked. On the other hand, I always surprised that you decide, well, you all work on the perception that the whole world is based on toxicity. And that's a very strange idea. I wonder why you keep on working on it. And I would like you to tell me what you think about those things. And above environment, I want to know, you know what's happening in around the world. And we have many wars, and they are throwing bombs all over the place. And there are many particles coming from these very high toxic things. And I would like to know how long those nanoparticles circulated around the Earth. How long do they stay? And how they affect us today, even in Denmark. Thank you.
Okay, that was 3 questions. First one about injections and blood-brain barrier. In terms of, okay, so there are 2 different fields. There's pharmacology and there's toxicology. So in pharmacology, you have people with a disease, so you will accept that they have some kind of risk of getting an adverse effect because you want to treat something, and you will say the benefit of treating this disease is greater than the potential adverse effects. You know that from all drugs, they will say maybe you get sick, but in 9 out of 10 people you will get better. Okay, so that's the first one. It may have been investigated, the blood-brain barrier, for different particles, because the particles in in this prescription you're talking about might be of the very soluble kind of particles. I could expect that, and I'm more into the metal stuff, but so it might be tested. That was the second question. Okay, also about blood-brain barrier. If you inject something, I suppose you inject it, but if you inject something into the bloodstream, normally particles will not last long in the bloodstream. Actually, the problem is that the half-time in the bloodstream circulating around the body is too low. So the problem is to create some particles that can actually go around the bloodstream for maybe 2 hours without being excreted somehow, or broken down or taken up by macrophages and stuff. But at the same time, they shouldn't be persistent and stay in the body forever, right? So that's a big question. If it has been approved for drugs, it should be okay, I would say. Yeah. It's cancer. Yeah, okay. So if you have cancer, you can have the decision between use this nano compound. We don't know if it has adverse effects, but if you don't get treated, maybe you will die in a month. So then you have, then the regulators are willing to take a higher risk compared to bisphenol A in baby bottles. You don't want the baby to be exposed to something, but if it's a cancer-dying person, you will do it. So that's kind of addressing your second question. And the last question, yeah, sorry. The last question was about bombing and nanoparticles. Normally, I wouldn't expect nanoparticles from the ground air to persist too long. I would expect them to become aggregated in the environment. But I don't know much about it. Fortunately, Frank is going to talk about jet engine exhaust. So he will know more about particles in air in real life situations. So I guess you should address this question to him later on today. Yeah. Sorry.
First of all, I'm not so sure that people's blood-brain barriers are still intact with the lifestyles that we have. That's for starters. And the nanoparticles are not tested in conjunction with other stuff that we are exposed to. For instance, I know that the asbestos will give cancer, but only when SV40 from the polio vaccines, the 40th simian monkey virus, is present in the body, which is a cancer virus. So you need two things to get this mesothelioma. Illness. Yeah.
It's true that many diseases are multifactorial. That was included in the...
But these nanoparticles are not tested in conjunction with other things. It's only looking at what they do.
Yeah, that's actually a very hot topic you touch upon there, because at the moment there's a big debate about endocrine disruptors or substances that affect the hormone system. And what people found, also groups at Aarhus University are working with, is because in the environment you're not just exposed to one endocrine disruptor, or it could be PCBs or whatever. You are always exposed to a mixture of different chemicals. So very hot topic within toxicology is actually mixture toxicology, but it's just so difficult because you have to add in different compounds. But the idea is that if you have this one compound and this one compound, and you're exposed to this one, you will have an effect. If you're exposed to this one, you will have an effect. But if you're exposed to both at the same time, you will have a much higher effect than the two of them should give combined. So there's some kind of synergistic effect. This is kind of illustrating. So on nanoparticles, we don't know anything about that yet. But we are looking into the dependence of different genotypes and stuff like that. I mean, what kind of DNA do you have, and does that affect? But yeah, that's yeah.
How does colloid silver fit in your discussion? Nanoparticles, are they smaller than colloid silver, or what? So many people are using colloid silver as antibiotics and antivirals.
Yeah.
Thank you.
That's a good question. Okay, so colloidal silver was introduced in the US already. Silver has been used as an antibacterial for ages, decades, hundreds of years. And in the late 19th century, they introduced colloidal silver in the US, and it was used as medication. Afterwards, we found out that colloidal silver actually usually contains silver nanoparticles. So you actually expose yourself to silver nanoparticles when you drink colloidal silver. But then again, there are many types, so they might found out a way to just produce micro-sized particles. Okay, but they have to be very small to be in the solution, right? How does it fit in? In general, we don't think that silver nanoparticles are very toxic to humans. But there's an ongoing debate, and University of Copenhagen may think different. But at least our results show that it might not be the big problem. The problem with silver nanoparticles is primarily the same problem as if you're exposed to every other silver compounds, that the worst thing that can happen is that you get this azuria, meaning a blue discoloration of the skin, and you will just turn blue for the rest of your life, right? You will. It's deposited in the skin. So, but you don't die from it. So, in my opinion, it's not dangerous to drink this. But this is my personal opinion, not our group opinion or something like that. I had one more comment, but the thing about it is that silver ions and silver nanoparticles are actually used in wound treatment several places. So one could speculate that if too many people drink silver-containing substances and it excretes silver, that microorganisms might become resistant to silver, and that would be a bad thing. But then again, that's benefits, plus minus, whatever. So, but in my opinion, it's not very dangerous.
I think in order to keep the time schedule, we would thank Rasmus for coming here. And